Leetcode number 70, climbing stairs. If you're like, what the hell? How is this an easy problem? Well, that's because this is a textbook dynamic programming problem. And in this video, I will teach you everything you need to know to solve these types of problems, including a few tips and guidelines you can follow. Let's jump right into it. We are climbing a staircase containing n stairs. At any given stair, we can either go up by 1 or by 2. Our task is to return the total number of distinct ways we can reach the top. So if we have one stair, we can go up by 1, so we only have one way to reach the top. If we have 2 stairs, we can go up by 1 twice, or we can go up by 2 once. So we have 2 distinct ways to reach the top. If we have 3 stairs, we have 3 different ways, and if we have 4 stairs, we have 5 distinct ways to reach the top. Counting the number of ways by drawing them is pretty straightforward, but writing a program to do it isn't quite as obvious. One way to figure it out is to start from the top. Let's say that we are on the stair number 4, and we want to go back down to the ground level. So on the 4th stair, we can go down by 2 or by 1. If we go down by 2, we can also go down by 1 or by 2. If we went down by 2, then we reached the ground and we found one way to climb the staircase. If instead we only went down by 1, then we can again go down by 1, which gives us one more way to climb the stairs. Now if we go back on stair 4 and go down by 1, we can repeat this process of either going down by 1 or by 2 until we discover all the different ways to go down the stairs. So here, what's important to notice is that the number of distinct ways to reach the 4th stair is equal to the number of ways to go on the 3rd stair, plus the number of ways to reach the 2nd stair. And the number of paths to reach the 3rd stair is equal to the number of ways to reach the 2nd stair plus the number of ways to reach the first one. So now it should be clear that we can define a function w of n that returns the number of distinct ways to reach the stair n such that w of n is equal to w of n minus 1 plus w of n minus 2. Knowing that we have the base cases w of 1 is equal to 1 and w of 2 is equal to 2. When we have a recurrence relation, it's pretty straightforward to convert it to code. We just need to define a new function, but let's rename it to climb stairs to match what Leetcode expects. Then we write down the base cases. So if n is equal to 1, then we return 1. And if n is equal to 2, we return 2. And finally, we return the result of the recursive calls. This works well until the execution time starts to grow exponentially. This can be explained by looking at the recursion tree. In this example, when we have only 6 stairs, we can see that we have already quite a lot of duplicated work. And that's when programming dynamic comes into play. Because you see, programming dynamic is all about overlapping subproblems. When you have a problem that can be broken down into subproblems which are reused several times, then we can use dynamic programming to avoid repeating work. The first technique we can use is called memoization, which consists in storing the result of intermediate calculations in, for example, a hash map. If we go back to the definition of our function w and we want to compute w of 6, then we will check if we can find its value inside the hash map, but it's empty for now. So we expand the left branch of the expression and we keep doing this until we reach a base case. We then can expand the right branch and we can store the result inside the hash map. And we do that for every intermediate result, so that when we need that value, we can just look inside the hash map and find it. So you can see that with this simple trick, we can considerably slim down the recursion tree. Let's look at a possible implementation, in which I define a hash map and a helper function that takes as arguments the number of stairs and the map. Inside this function, we start by handling the base cases, and then we check inside the map if we already know the answer. If we don't, we compute it and store the result inside the map before returning it. Finally, inside the climb stairs function, we return the result of calling this helper function. And that's pretty much it for memoization. This technique is also referred to as the top-down approach, because we start from what we want, the top of the recursion tree, and we go down to the bottom, or the base case. So if this is called the top-down approach, there has to be a bottom-up approach, which is also called tabulation, which comes from the word tabulate, meaning to show information in the form of a table. If we go back to the definition of our function w, we can construct a table where the cell at index n contains the value w of n, and we can initialize the first two cells with the base cases, such that the cell at index 1 contains 1 and the cell at index 2 contains 2. Then for each remaining cell, we can calculate its value by adding the values of the two previous ones. So that's what we do until we reach the value we want. If we look at an implementation, we can start by creating a table of size n plus 1, then initialize the first two cells, then we fill the rest of the table, and finally we return the last element of the table, which corresponds to the final result. So here we clearly start from the bottom, or the base cases, and go up to the top, or the result we want. Pretty good, right? Well, we can do better than that. You see here, we only need to remember the two previous values, so we can get rid of the array and use a few variables instead. So now we have linear time and constant space complexity. It doesn't get better than that. Indeed, this final solution is faster than the one with memoization, but this difference is insignificant compared to the one with the original recursive solution. This really highlights that when it comes to performances, the algorithm is king. Dynamic programming allowed us to convert an impossible problem to compute to a very fast one. Okay, now that you know about dynamic programming, let me give you a few guidelines that can help you solve dynamic programming problems. So first, if you can, try to identify that you are dealing with a dynamic programming problem. To be able to do that, there's no secret. You have to practice. You can also read this great article that highlights 5 dynamic programming patterns, which can definitely help you recognize and solve more problems. Be careful though, sometimes problems sound and look like dynamic programming problems, but they can be solved with better and faster techniques. Okay, then you want to find the recurrence relation. This is the difficult part. It involves finding the subproblems. You need to figure out how to break down the problem into smaller subproblems and see how they interact with each other. You need to find the right representation, and that's what can be really difficult to do. But I guess that's true for problem solving in general. So if you're able to express the problem using recursion, you can start optimizing it using memoization. And I recommend you to start with memoization because it's usually easier to do, but nothing is stopping you from skipping all these steps and starting right away with tabulation. If you make it to this point, see if you can apply some final tricks to minimize the memory consumption like we did by using variables instead of an array. If you're able to do all this, then you're good to go. But I think that stopping at step 2 should be enough in most cases. The real challenge is to find the subproblems. So keep practicing, don't give up, you got this. And that's all for today. Don't forget to subscribe so my channel can go subscribe so I can get subscribers. Subscribe and like and comment and share my videos and watch it again and again and again. Anyway, yeah, well, that's that.